Developing a workable theory of quantum gravity remains a significant challenge, particularly when extending double field theory beyond cubic order. Double field theory, a promising subsector of string theory, encompasses universal massless fields and all their massive Kaluza-Klein and winding modes. However, implementing the weak constraint in a non-trivial manner is crucial to extend the theory to quartic order. In contrast, strongly constrained DFT, a reformulation of general relativity coupled to B-field and dilaton, has found applications in double copy and exceptional field theory. Despite its limitations, strongly constrained DFT has shed light on the potential of double field theory in addressing the complexities of quantum gravity. This paper presents a breakthrough in constructing weakly constrained double field theory to quartic order. By overcoming the obstacles posed by the weak constraint, the authors have successfully extended the theory, providing a more comprehensive framework for understanding quantum gravity. The detailed proofs supporting this construction will be published separately, offering a valuable resource for researchers seeking to build upon this innovative work. The implications of this achievement are far-reaching, as weakly constrained double field theory has the potential to reconcile the principles of general relativity and quantum mechanics, ultimately contributing to a more unified understanding of the universe. Yang-Mills theory can be encoded in an L-infinity algebra, a homotopy Lie or L-infinity algebra, constructed on a graded vector space. This space is comprised of subspaces containing gauge parameters, fields, field equations, and Noether identities. The gauge algebra, nonlinear interactions, and other features are described by multilinear brackets Bn. The action for field psi is given by an integral over spacetime, involving auxiliary fields phi a and structure constants fabc of the color Lie algebra G. This action exhibits quadratic relations, ensuring perturbative consistency of the classical theory. The L-infinity algebra is constructed on K circled times G, where K is a C-infinity algebra with a homotopy generalization of a commutative associative algebra structure. The non-vanishing products in this algebra are an operator M1 of degree +1, a bilinear product M2 of degree 0, and a trilinear product M3 of degree 1. These products satisfy quadratic relations, guaranteeing consistency. This construction is crucial for understanding the double copy of Yang-Mills theory and its relation to gravity. The L-infinity algebra provides a framework for exploring the intricate connections between gauge theory and gravity, offering insights into the underlying structure of these fundamental forces. The authors discuss the algebraic structure of Yang-Mills theory, focusing on the C-infinity algebra and its extension to the BV-square-infinity algebra. The C-infinity algebra is defined by the products M1, M2, and M3, which satisfies certain graded symmetry properties. Specifically, M2 is graded symmetric, while M3 is symmetric in its first two arguments and vanishes under total graded symmetrization. The authors provide an example of the two product between fields, denoted by M2, which is equivalent to the dot product of two fields. The L-infinity algebra structure is defined on the tensor product K circled times G, where K is the space of fields and G is the Lie algebra of the gauge group. The authors introduce the Bn operators, which encode the L-infinity structure, and provide formulas for B1 and B2. The C-infinity relations and Jacobi identities ensure gauge covariance of the theory. The authors then introduce the BV-square-infinity algebra, which is a richer structure that plays a crucial role in the double copy construction. The B operator is a second differential that acts on K and satisfies certain defining relations, including B2 equals 0 and Bm1 plus M1b equals square. The B operator is not compatible with the C-infinity algebra, and its failure to act as a derivation on the product M2 defines a new Lie type bracket B2. The authors discuss the compatibility between B2 and M2, which holds only up to homotopy and square deformations. They introduce operators ds and d squared to keep track of such square failures in bilinear and trilinear maps. The Leibniz relation between M1 and B2 is deformed by a term involving M2 and d square, and the Jacobi identity of B2 holds up to homotopy and up to a square deformation. Overall, this page sets the stage for the development of the BV-square-infinity algebra in the context of Yang-Mills theory, highlighting the intricate algebraic structures and relations that govern this framework. The authors elaborate on the BV, square infinity algebra on K and its extension to the tensor product KK. They introduce the vector space X, equipped with two combinations of Laplacians and two possible B operators. The vector space VDFT, carrying the L-infinity algebra of weakly constrained DFT, is defined as the linear subspace of X annihilated by both increment and B-. On X, the authors establish relevant algebraic structures, including a nilpotent differential and a two-product, which form a C-infinity algebra. This C-infinity algebra is part of a larger, BV-type, algebra, featuring a BV increment infinity algebra on X. The increment minus deformations act on this algebra, and the authors discuss the two-bracket B2 and its relation to the Poisson compatibility. Employing the homotopy transfer, the authors define a BV increment infinity algebra on Kerr increment and further restrict it to Kerr minus, where only the L-infinity subsector survives. For the special case of a doubled Euclidean torus, the projector P increment onto Kerr increment is defined. The construction of the three-bracket for weakly constrained DFT on a torus begins by defining a homotopy map, H, which is a degree 1 operator obeying a specific equation. The homotopy transferred maps are computed systematically, emphasizing that the BV infinity algebra is not transported to an undeformed BV infinity on Kerr increment. The obstruction, O, arises from the homotopy-Jacobi identity of B2 being obstructed. It is shown that O is B1- exact and can be inverted, leading to an unobstructed L-infinity algebra. The paper concludes by describing the construction of the three-bracket, introducing a new non-locality due to the Laplacian increment plus, highlighting its importance and setting the stage for the next section's computation of the explicit three brackets for the gauge algebra. In higher gauge theory, the gauge algebra is encoded in the homotopy-Jacobi relation, a fundamental concept that ensures gauge transformations form a closed algebra. This relation is defined in terms of the Jacobiator, a mathematical object that encodes the algebraic structure of gauge transformations. The Jacobiator is a function of three gauge parameters, taking values in the space of gauge parameters. To verify the homotopy-Jacobi relation, specific components of the higher gauge structure B3 must be computed, including its action on gauge parameters and fields. For example, evaluating B3 on three gauge parameters yields an expression that contributes to the homotopy-Jacobi relation. Similarly, evaluating B3 on two gauge parameters and a field gives rise to another expression, which can be simplified using the Leibniz rule and the weak constraint to cancel non-locality. This simplification is crucial for maintaining the gauge algebra structure in higher gauge theory. The homotopy-Jacobi relation is essential for ensuring that the composition of gauge transformations also results in a gauge transformation. Computing this relation in the context of higher gauge theory reveals intricate mathematical structures and the interplay between different gauge parameters and fields. This computation demonstrates how the gauge algebra can be encoded in the homotopy-Jacobi relation, providing insights into the nature of gauge transformations and their algebraic properties. The construction of a weakly constrained double field theory to quartic order with all dimensions toroidal and doubled is discussed. This theory remains to be generalized to Lorentzian backgrounds and cosmological backgrounds. Extending the construction to all orders requires an improved understanding of the kinematic algebra of Yang-Mills theory. There is also interest in extending this to exceptional field theory and genuine M-theory modes. Quantum action and field theory, an overview of recent research. In the realm of theoretical physics, recent studies have delved into the intricacies of quantum action, field theory, and their interconnections. A pivotal contribution comes from Olaf Hohm and Barton Zwiebach, who explored L-infinity algebras and its implications for field theory. This work has significant implications for understanding the structure of gauge theories and string theory. Another key area of research is conformal field theory, with notable contributions by Anton M. Zeitlin. His work sheds light on the symmetries and properties of these theories, which are crucial in various areas of physics, including condensed matter and particle physics. The concept of homotopy BV algebras has also garnered attention, particularly through the work of Michael Reiterer. This research provides a new perspective on the algebraic structure underlying quantum field theories, offering insights into their symmetries and interactions. Furthermore, Larin-Borston et al.'s studies on the double copy from homotopy algebras have revealed intriguing connections between gauge theory and gravity. This research could potentially bridge the gap between these two fundamental forces, advancing our understanding of the universe. Roberto Bonezzi et al.'s investigations into the gauge structure of double field theory have shed light on the geometric and algebraic properties of this framework. Double field theory is a promising approach that attempts to unify two seemingly disparate areas of physics: general relativity and string theory. Lastly, Moore-Benshahar's work on 10D super-Yang-Mills scattering amplitudes offers a fresh perspective on high-energy particle interactions. This research is vital for comprehending the behavior of particles at extremely high energies, potentially shedding light on the nature of fundamental forces and the universe itself. These papers collectively represent a significant advancement in our comprehension of quantum action and field theory, pushing the boundaries of our knowledge in theoretical physics.